Right. Thank you for the introduction, Annie, and thank you for plugging our annual symposium. It wouldn't have been what it's become without your participation and support. I'd also like to thank the rest of the organizers for inviting me to talk at this event. I have very fond memories from a similar event, IPAM event, that was held in 2011. I was a graduate student at the time, and those interactions and the talks that I attended have had an impact on my research since, including to some extent what I'm going to present today. So again, thank you to the organizers. So getting to the subject of my presentation is about network control, so traffic light control at the network level. And I'm going to talk about decentralized, a particular decentralized technique, and how what happens when you combine it with continuum traffic flow models, how you can overcome some of the limitations, but that combination also brings some challenges along with it. All right. Oops. Here's the outline of my talk. I will first talk about the backpressure algorithm. So that's the decentralized approach I'm going to talk about. It has also been known as the max pressure algorithm, or sometimes it's referred to as the max weight algorithm. It's a particularly simple approach for calculating or assigning a priority to different streams of traffic at signalized intersections. So I'm going to talk about that. I'll use a small example to illustrate how it works. And from there, I'll jump into some of the performance guarantees that you get at the network level, specifically stability, using Lyapunov optimization techniques. I'll then talk about some of the shortcomings that come with the standard approach, the standard backpressure technique, and how you can overcome some of them by using continuum modeling approaches. Okay. So to give you a quick background, the backpressure algorithm was discovered by Tessioulas and Ephraimidis in 1992, and their work or their motivation was packet routing in wireless networks. And so what they were looking at was different nodes in a communications network that need to communicate, where the channels interfered with one another. So you're trying to pick a bundle of channels that you can activate at any one time that do not interfere in such a way that would achieve certain objectives. Now, it took about 10 years, but 10 years later, two independent papers or two independent groups of researchers adapted the backpressure approach to traffic signal control. So they saw the analogy between the interference pattern between channels in wireless networks, and how you have basically the same thing in traffic signal networks. So those two groups were Wongpironmsarn et al. and Praveen Varaiya, 2013. So they did this independently. And since then, there have been many variants of the approach that was presented in these two papers. Some variants included things like optimized signal timing with route guidance. Some specialized the approach that was here to include constraints, real world constraints that traffic engineers care about, like fixed phasing sequences, or optimizing over travel times as opposed to queue sizes, and so forth. A notable one came out early this year by Jack Haddad and his team at Technion, and they implemented the approach in the real world. And so they did a live test, and the figure that I have here on the right comes from that live test. The purple lines are previous days, so days when the back pressure approach was not applied. The black line is what you get, or the travel times that you get when you apply back pressure, and they activated it in this for almost 2 hours. So this gray shaded area is when it was active. And for these points, it sort of outperformed the previous days. You can at least say that it's comparable. Here, it didn't do very well at this point in time, and they chalked this up to an incident that was at the site. So that's why you see a little spike here. But the takeaway is that this is something that you can actually deploy in the real world. Okay, so that's a takeaway from that study. Now, the reason these approaches are attractive is, first, it's a decentralized approach, meaning you can implement it at each intersection controller independently of the other one, of the next one, and what you get is guarantees at the network level. So it's easy. So you get easy computations. It's very computable. And it turns out that feature is specific to road networks. So that's not something that's inherited from wireless networks. Another feature that is often cited is the fact that you don't really need to know what the arrival rate. So it's robust to changes in demand. Okay, so that's the background. What I'll do next is illustrate how it works. I'm going to use this example in the coming slides, in this slide and the next coming slides, to illustrate some of the main ideas underlying the back pressure algorithm. So let's consider this to be the network. So I have only one intersection in my network. And we're trying to, and we only have two phases. So we have an eastbound movement going from link A to link B, and then I have a northbound movement going from from A to C, and then B to D is the northbound movement. And we're trying to pick, or the back pressure algorithm gives you a way to pick which phase to activate at this network, at this intersection. And the way it does it is by solving this very simple optimization algorithm, right? So what these terms are, these are called the movement pressures. Basically, it's the product of the saturation flow rate, which is the maximum number of vehicles that you can pump out of the inbound link over time. And this is a weight, and the weight is calculated based on the queue sizes. So sometimes this is interpreted as a throughput maximization objective, but considering the weights are not necessarily throughput related to the throughput, they're related to the differences in the queues. That interpretation may not be entirely accurate. Okay, so it plays the weights play a major role. And so the way the weights are calculated is by looking at the queue sizes. So let's take this approach where, so for this movement, the difference, or the weight, would be 5 minus 2. So the inbound queue minus the queue on the outbound link. And that's the pressure associated with this movement. So the weight would be 3. Similarly, for the northbound movement, the weight would be 1. Now, if we assume that the saturation flow rates are the same, what the back pressure algorithm will do is it'll say pick P1, okay? So that's the idea. It just performs this very simple calculation. All right, at a regular intersection where you have 16 different kinds of movements, you have four-leg intersection, where now you're trying to pick bundles of movements or phases, right? These would be non-conflicting flows, or you can allow something like this where you have a permitted and a protected movement, but it's easy to determine which one gets the lion's share of the capacity. So the protected movement gets the lion's share. A right turn like this would use gaps that are made available in traffic, in this opposing traffic stream. So you decide on these beforehand, and that's pretty simple. And now the pressure, or the phase pressure, is the sum of the constituent movement pressures. So you just add them up, and then you pick the phase that gives you the largest phase pressure. okay? And the weights are still calculated based on the differences in the queue sizes. Now, going to the intersection level, what happens is you sum over all phases throughout the entire intersection. So this P is now a network phasing scheme. So it has, so for this network, this would have 11 elements, one for each intersection, telling us, so after we solve it, which phase to activate at each of the 11 intersections. Okay, now we take an argmax over all possible combinations of phases across the intersections. And the nice thing about traffic networks, and this, again, this is not something that you get with wireless networks, is that movements at different intersections do not interfere with one another. They don't conflict with one another. So there's nothing to stop me from activating any phase at this intersection and then another phase at this intersection. And so what that buys us is the fact that we can, the argument that maximizes this is the argument that maximizes this, meaning I can take the argmax inside the outer sum, and I can parallelize this calculation. So we can do an argmax for each intersection separately. And so the problem naturally decomposes by intersection at the network level, and that's the desirable feature of this algorithm. Another desirable feature is the fact that we don't really need to know how many vehicles are arriving to each intersection. So each controller is basically looking at conditions in its immediate vicinity and making decisions about what traffic stream to prioritize based on that knowledge. It doesn't require any other knowledge, and that's the advantage of this approach. What it comes with really is stability or performance guarantees, stability guarantees at the network level. And to illustrate what we mean by that is basically this condition here. So if we employ the backpressure algorithm, we can guarantee that this condition will hold true. And this condition basically says that the network queues will not grow indefinitely if we use the backpressure technique. So it adapts to varying traffic conditions. Now the dynamic, so let's take the dynamics at the level of this small network. What I want to illustrate is this notion of a capacity region, which is the types of arrival rates that you can accommodate. So it's important to note that yes, it works. Yes, it prevents queues from growing indefinitely, but that only works if the arrival rates fall within a particular region. So it doesn't work for any arrival rates. And that set of arrival rates is referred to as the capacity region of the network. And it's basically the arrival rates that respect this condition over here. So basically the expected departures from the queue are greater than the expected arrivals. So if the expected arrivals are within a region or a set of flows that I can accommodate, where the outflows are going to be greater than the inflows, then clearly the queues will not grow indefinitely. So basically what we're after is for this to be greater than this, okay? And so to illustrate what the capacity region looks like, so let's say we activate phase one. So this is how it relates to the control variables. If we activate phase one, the eastbound movement, then I can accommodate inflows to the network that fall within this blue set here, just this line, meaning lambda or the arrival rates to the other intersection, to link B, has to be zero. Any arrival rate greater than zero is outside of the capacity region if all I have is this phase one. Similarly, if I activate phase two, then I can accommodate arrivals that are within this set, anything along this line up to the saturation flow rate of the second movement. All right, and I can also accommodate arrivals that fall within the convex hull of these two sets, meaning by switching between P1 and P2, I can accommodate flows that fall along this line and under this line. So any arrival that's, let's say, 50% of the saturation flow of B and 50% of the saturation flow of A, I can accommodate by switching, by spending half my time accommodating the inflows from this direction and half my time accommodating flows from this direction. Okay, so that's the idea behind the capacity region. And the important thing to note is that if you have an arrival that falls outside of the capacity region, then there is no phasing scheme at all that can stabilize the network. So if you have an arrival that's outside of this region, the queues will grow indefinitely, and that's something that's inevitable. So that's the idea. All right, now going to the network level, what happens is we have arrivals from outside of the network. So these are stochastic arrivals. And we also have arrivals from inside of the network. So we have endogenous arrivals and exogenous arrivals. That makes matters a little bit more complicated because now that condition that I wanted to check where the average departure is greater than the average arrivals depends not only on what I'm doing at the intersection related to link I, but at other intersections as well. Okay, so the flow rate, this lambda, is depends on what I'm doing at the intersection, and well, here it's only going to depend on intersection, the downstream end of link I, but here these flow rates will depend on what I'm doing at other intersections. Okay, so to analyze the stability in this case, so for let me just go back real quick. So for this case, for the simple case, all I needed to check was, is my arrival rate vector smaller than what I can push through the intersection? That's all I had to check. Here it gets a little more complicated. And what we do is use a Lyapunov optimization approach. And so just to, if you don't know what a Lyapunov function is, it's just a function that takes in the state of the system, and it measures the size of that state or the energy in that state, if you will. Basically, it's a positive function. It's and what you want for it to do is to decrease with time. So here's one example. So this is the one that's widely used in all of the traffic literature, all of the back pressure and traffic literature. And so what we want is for this function to decrease with time, right? So if the queues are shrinking, then my Lyapunov function is going to be shrinking as well. And because this is a discrete time method, we're going to use this drift technique. So we're looking at the difference between the energy at time at the next time step minus the previous time step. If this was a continuous time system, which we'll see later on, we'd use the derivative with respect to time. Okay, and we use the Lyapunov drift condition to check stability. So if this is true, if this condition holds true, then this guarantees that this is true. Okay, so and the way to do that, I mean, to prove it, it's pretty straightforward. It just takes a few steps. It's in more than one of the papers that you'll see in the transportation literature. But here's what it says. It says that if you can find, well, this is a conditional expectation with respect to the state at time t. So if I'm measuring the state at time t, and so that's what the controllers are doing. And then if the drift is bounded from above by a constant minus another constant multiplied by the sum of all the q sizes, then we say the system, for all t, then the system is said to be strongly stable. So the key is we need to find two constants, b and epsilon, that don't depend on time, that don't depend on the state, that's important, and don't depend on the arrival rates. If we can find such constants where this inequality holds true, then we say that the system is strongly stable. Okay, this B, and on this talk, I'm not really going to talk much about this B. It simply follows from second order conditions on the exogenous arrivals and these flow rates. Okay, so if these are bounded, if these have bounded second moments, you can immediately get this constant. And that's related more to, so if you have bounded variance, it's related more to the traffic, the way you set up the model than anything else. And for flow rates and traffic, it will be, the second moments will be bounded. That's well known. This is a little more. This is not as intuitive. So this is a measure of well, it's a bound on the difference between the outflows and the sum of inflows. That's what this captures. Okay, so to show you how this works, so if we can use these definitions to arrive at this inequality. So you simply take the Q, you square it, and then you square both sides. You take the sum over all lengths, you multiply by 1/2, and you move. You do some simple manipulations. You take the conditional expectation with respect to the Q size, and you arrive at this inequality. So it's just a series of manipulations, but you get it quite easily. Now, let's say that there exists a policy. Okay, so there exists some sort of a control policy that will stabilize the network. If there does not exist such a policy, then really there's nothing that you can do. But let's say that there is something out there that will stabilize the network. We don't really need to know what it is. We just need to know that it exists, and it can require a lot of information. It can require things we don't want to have to measure. It just has to exist. So if it does, then we say that well, then the drift condition holds because we have this epsilon, this non-negative epsilon or positive epsilon constant that doesn't depend on the arrival rates or the state where this equality holds. And now if you compare these two, this inequality holds, sorry, and if you compare these two, you'll see that you can reconcile this with this. So basically this can be thought of as a lower bound on this second term, so the terms inside the brackets here, okay? And then from here, what we can do is optimize. So then if I maximize this, I know I can always beat this over here by maximizing. So if this is associated, if this constant is associated with a specific P that I would put in, I don't know what P it would be. It would be something that the policy would tell me. But as long as it exists, then I know that I could beat this by maximizing, right? So I can find another policy that will maximize this, and then that will give me, that will bound this term from above, meaning I can simply use the constant that I have with the existing policy. So this is a feasibility argument. As long as the problem is feasible, all I need to do is solve this optimization problem, and I get something that will stabilize the network. That's basically what this says. And since I really don't care about the maximum itself, what I really care about is the argument that maximizes this. What I'm looking for is the control setting. You can take this out of the equation. So the average arrival rate, it's a constant. And then by rearranging terms, you get the form that we saw earlier on. So that's where this comes from, right? So this step is how we get rid of the arrival rates. This is why we don't really need to know what the arrival rates are. And then rearranging terms here, we get the optimization problem that we need to solve at the network level. And then as we saw, this decomposes naturally by node, okay? So that's the standard back pressure. It does come with some shortcomings. One specific shortcoming is that we're using point Qs to represent it, so it doesn't really know about it doesn't care how vehicles are distributed spatially. And in order to analyze stability, we need to allow for the capacities to be infinite. And so as a result of that, you can't capture spillback. And spillback are a very important feature for signalized intersection. So that's one of the drawbacks, is that it doesn't do very well when you have spillback. And I'm illustrating that in this simulation here. But another way to see it is by looking at these two pictures. So let's say we're calculating the weight based on, let's say this is link J. Now in both of these pictures, you have the exact same number of vehicles. So the queue size is 9 in both cases. But what you should do in this case and what you should do in this case are two very different things. So here you know that if you activate an incoming phase, that's just going to create gridlock and spillback, whereas here you have room. So it's important to account for how vehicles are distributed spatially along the length of the link. And that's something we can overcome with continuum modeling. So by accounting for how vehicles are distributed spatially along the link. And that's what I'm going to do. So I'm going to use, so for this talk, we're going to use the LWR model, but that's without loss of generality. It doesn't matter what continuum model you use. The idea is that we want to capture the spatial distribution of vehicles along the link. So there's a conservation equation, the standard LWR model, where rho tells us what the vehicle density is at position X along the link at time t, and this is the flow rate. And for the flow rate, we're using a fundamental diagram. Well, in this work, we use the stochastic fundamental diagram. Okay, so that's where the stochasticity comes from in our paper. And now for flows across links, so that's the dynamics inside the links. The dynamics across links are, this comes from a simple node model where you're looking at the minimum of the demand at the upstream end and the supply, at the demand at the downstream end of the incoming link and the supply at the upstream end of the outbound link. Okay, and you take the minimum of those two, and then you multiply it by an indicator that tells you whether or not the phase is active. Okay. And these are so the demand and the supply function that basically come from the fundamental diagram, but this is the supply function pertaining to this link, and this is the demand function pertaining to this link. This tells us how many vehicles we can push out. This tells us how many vehicles we have space for in the downstream end, and then we multiply it by this indicator that tells us whether or not we can actually move vehicles between these two links. All right, now getting around the infinite capacity problem is easily done with a modeling trick. So if we're using LWR, we don't have infinite capacities, and there's no point to studying stability because the queue sizes are always going to be finite, right? So we do need reservoirs that will allow queues to build up indefinitely. And the way we do that is with a simple modeling trick. So we use a hybrid model where we have an LWR on the physical links of the network, and then wherever I have an exogenous inflow, we introduce a fictitious source link. Okay, so this captures arrivals from outside of the network. If it's taking place inside the network, then we introduce a node and we create a fictitious link that can hold as many vehicles as it needs to. Okay, so now an instability is interpreted as queues growing indefinitely along these fictitious source links. And we can allow these to be point queues. So we use basically a point queuing model so I'm switching now to continuous time because I'm using an LWR model for my physical link dynamics. These are the exogenous arrivals, and these are the departures from the link. And because we're not giving it these fictitious arcs, we're not giving them any spatial extent. I'm just dropping the x from the argument of the row function. Okay, so that's how we get around the issue with infinite capacities. Now, stability is interpreted as queues not growing indefinitely along the sources. So that's key. Otherwise, it's basically the same thing that we had before. And what we consider here is the following Lyapunov functional, because it's a function of really a set of curves here. So these are, so a density is not a point. A link density is an entire curve over, the length of the link. So it's really a functional. And what we consider is something that a weighted correlation function, right? So we integrate over space, and we take the product of the density at two different points along each link. And the weight we chose to use, you can use any weight that is non-negative, strictly positive, ideally. But the idea behind it is that we want for the weights to be higher when the densities are at the boundaries of the links, because that's what I care about. Okay. All right, and now the stability condition is, so now we're operating in continuous time. We're conditioning with respect to the network traffic densities, and then we integrate. So this is basically a queue along the link, right? So if we integrate the densities over space, you basically get a queue size. Otherwise, it's the same Lyapunov drift condition. And we want this to be true for all time. So we need to find an epsilon and a B. And these are found in almost basically the same kinds of steps. So B has to do with the second moments of the flow rates and the exogenous arrivals. Epsilon is determined using the same kinds of techniques that I described earlier. So if we do the derivation, right, here's what we get. So we get a weight function that, so instead of having the inbound queue size and the outbound queue size, we have a weighted version of the inbound queue and the outbound queue. So for the outbound queue, it's going to assign heavier weight to densities that are near the entrance of the link. And for the inbound queue, it's going to assign heavier weight to densities that are at the exit of the inbound link, right? So for this link, we care about densities here. We don't really care about densities that are all the way out towards the end of the link. And it's the opposite of that for the downstream link, because if I have heavy density at the entrance, that means that I can expect spillback dynamics, right? And here, if I don't have a heavy density here, then the flow rate out, I'm going to have small demand at the entrance at that point in time. And what we showed was that as long as the arrival rates are within the capacity region of the network, which is determined by the phasing scheme that I am, so the number of phases that I have in the network, then solving this maximization problem will ensure strong stability of the network traffic, okay? All right, so I'll just show you a couple of examples. So this is that heavy traffic example. And by heavy traffic, I just mean a lot of cars, not the queuing literature heavy traffic. So we have a lot of vehicles, we have heavy traffic here. And what we're seeing is because standard backpressure cannot differentiate between the spillback conditions and no spillback conditions, it keeps assigning green to this approach when it would do better to allow vehicles along the minor to go. And this is something that I just include in continuum modeling, the model can see, and it knows to relieve the minor approach when it can't accommodate all the traffic coming in through the major approach. And this is because the flow rates are downstream supply aware, right? So that's something that comes with the way we model this, the flow rates. And this becomes a little more pronounced if I have an incident. So here we're simulating a situation where there's a traffic incident over here. So the downstream queue size is relatively small. And so the standard backpressure will assign green to this approach, even though vehicles cannot move from here to here. Whereas here, it can see that there's no supply. So it'll try to starve this approach to allow vehicles to move along. So that's one of the benefits of incorporating or looking at how vehicles are distributed along the spatial dimension of the network. Here's another example where we've created an upstream incident. And in this case, the demands are low, but the queue sizes are large. The demands at the entrance are low, but again, the queue sizes are large. So the standard back pressure will still assign green, will still prefer this movement over the minor, where our position weighted back pressure will allow vehicles to move across the intersection along the minor, to relieve the minor. And it does this automatically. Okay, and this is because, again, it's because it's upstream demand aware. And so this is another set of tests that we did where we wanted to see what happens if you do introduce an incident somewhere, and how does the impact of the incident propagate spatially in the network under back pressure versus under position weighted back pressure. And what we wanted to see was how graceful it is once the incident goes away. So this is an example of an arrival rate that is outside of the capacity region of the network. So there's really nothing you could do. Congestion is just going to have to build up. But the question is, once you take care of the incident, do the traffic lights operate in such a way that will gracefully go back to smooth flowing conditions? And we see that towards the end, after the incident goes away, that under position weighted back pressure, yes, indeed, the queues dissipate, whereas at the end of the simulation, under standard back pressure, you still have resilient, you still have queues that not resilient queues, but you still have queues that have formed that haven't gone away. But if you run this a lot longer, the queues will eventually go away under standard back pressure, but it seems to be faster under position weighted back pressure by just accommodating some of these additional features. So the last thing I'll talk about is two limitations of this approach. You can think of these as perhaps open questions that need to be addressed. One of the common criticisms is that you need to know what the queue sizes are in order for this to work. And that's not readily available. So if loop detectors don't report queue sizes, they'll tell you, occupancies and flows. And if you go to a position weighted back pressure, now we're demanding density profiles, not just queue sizes, which is a lot harder. What we did here was we combined, in a recent paper, we combined back pressure with a traffic state estimation technique, specifically an interpolation technique proposed by Treiber, so just a textbook approach. And what we saw was if we estimate the queue sizes or the queue profiles using this approach, we still do pretty well. So this is the real world delay profile at this one intersection in Abu Dhabi. And what we're seeing is at 20%, so this uses probe vehicles. So we simulated our approach to probe vehicles. This is the real world delay. And at 20% penetration rate, which is consistent with what you tend to see in the literature, we saw consistent good performance. Below that, and it's not really consistent. Above that, it's going to perform very well, and that's kind of consistent with the traffic state estimation literature. It says, 20% probe penetration rates, you get good estimates of traffic conditions. Beyond that or below that, you don't really get very good estimates. We're seeing better and better results in the traffic state estimation literature with some of the AI techniques that they're using now. The other drawback is that the stability result that we're proving is an asymptotic result, meaning that if you use it, it will stabilize the network eventually, not immediately, and that could be problematic. Well, how fast does it stabilize the network? Simulation experiments suggest that this happens at a reasonable rate, but we don't really have any analytical insight into how fast the stability takes place. And the reason this is important is because of all of the variants that are being proposed, where you might choose a fixed phasing sequence, or you might introduce other constraints that might slow down this stabilization process, and how it stabilizes becomes an open question in this context. Before I close, I'd like to acknowledge my PhD student, Li, who is currently a PhD candidate. She'll be a PhD, she'll be defending next semester. She did all the work. If you enjoyed this talk, she's the one that deserves all of the praise. If you didn't, then I'm the one to blame. And thank you for listening. So that's 40 minutes.
Thank you very much, Saif.